Hi guys, and welcome back. Finally we get into that question you've all
Casey
been...
questions.
Yeah.
Everybody's been going, phoning, our lines are going all the time.
I
Casey
keep saying
questions,
we're getting
Casey
onto
questions.
it, we're getting onto it.
All right,
Yeah.
so the big moment has arrived.
Yeah.
Okay, for this specific one, we're going to look at the February-March paper for 2010, and we're looking at question 8. Let's just get some color over there. So we're looking at question 8 over here. It's a bit of a lengthy one, so let's stay focused and pay attention to what we're doing. Now, they tell us that the combustion in air at high temperature produces oxides of nitrogen, which include nitrogen dioxide, and this is the most common one. Natural resources or natural sources of nitrogen dioxide include lightning and the activity of some soil bacteria. Now, these natural sources are small compared to the emissions caused by human activity. Nitrogen dioxide can irritate the lungs and cause respiratory infections. Also, when NO2 dissolves in rainwater, it forms nitric acid, which contributes to acid rain. Now, just by going through that specific section over there, you can see that they're talking about quite a few activities in nature that will affect the production of nitrogen dioxide, as well as some of the human activities. Now, they ask over here for us to state 2 human activities that will contribute to the high nitrogen dioxide levels in the atmosphere. Now, just a very quick reminder, when you go and you do the whole section on fertilizers, one of the key things that we teach you over there is that nitrogen is very unreactive. Remember, nitrogen bonds with itself and forms a triple bond between one nitrogen and another nitrogen, so it's a triple bond over there. And this triple bond requires a lot of energy to be broken. And that is why lightning is needed in nature to form nitrogen dioxide. It's called one of your nitrification processes. All right, so lightning releases a lot of energy and also a change in pressure. So there's extremely high pressure, a lot of energy, and that is how the nitrogen is then broken apart and it bonds with the oxygen to form the nitrogen dioxide over there. And it also forms other nitrates that can then be dissolved in the soil and plants can take them up. But in human processes, we've got a couple of industries and a couple of our activities that contribute and help us to produce nitrogen dioxide. Not that it's necessarily always a good thing, because it is a pollutant. All right, now the first thing over here that we can look at is factories and industries. That produce nitrogen dioxide as a byproduct. Right, now this product is obviously a pollutant because it doesn't really help. It gets released into the air. The next one is the burning of coal. Now in South Africa, you would know that our biggest source of electrical energy is coal burning power stations. So the burning of coal, over here, work on my spelling for today. So the burning of coal in power stations will contribute to that. All right, and then the last one, and unfortunately, I'm definitely a contributor to that, and I'm sure Indiana as well, because we all drive cars. Yeah. All right, cars. So in the car, while you're driving the car, cars burning fuel will produce NO2 gas. All right, and this is a very big pollutant over there. So that's your question over there. You'll see that it's 2 marks. Now, any one of these 3 points that I've mentioned over here would be able to give you your 2 marks over there. They didn't ask you, or they asked for 2 activities, so any 2, you could have given those 2 or that one, as long as you give us 2 over there. Now, for 8.2, they go and they ask us to give a balanced equation to show how nitric acid forms with nitrogen dioxide in air. There's 2 different processes. I'm going to give you both reactions over here. Now, the first one is where you have NO2. Remember that this is in the gas form. And when it rains, this reacts with the rainwater, which is H2L in the liquid form, H2O in the liquid form, not H2L. This then produces HNO3, which is your nitric acid. So there's your HNO3, and this is in an aqueous solution. But it also produces nitrogen oxide over here. If you go and you balance this one, we will see that I've got over here 2 nitrogens, 1 over here, and I'm going to need to balance my hydrogens as well. Let's balance the hydrogens first. I see that I've only got 1 hydrogen on this side, 2, and I bring in the 2 in front. A good tip that I always give my students is to go and balance your hydrogens and oxygens first. So now I've balanced my hydrogens, I've got 2 on either side. Now I go and look at my oxygens. There are 3 oxygens multiplied by the 2, which gives me 6 oxygens, plus the 1 is going to be 7. So over here I've got 1 oxygen. If I go and put a number in front over here, it's going to affect my hydrogens, and I don't want to do that because I've already balanced it. So I'm now looking to my nitrogen dioxide. So if I bring in a 3 over here, it would mean that I have 3 times 2 would give me 6 oxygens, plus the 1 over there is 7. So now I see that my oxygens are balanced, and lo and behold, if I go and I look, 2 times the 1 for my nitrogen over there, now I've got 2 nitrogens, plus 1 is going to give me 3, and there's the 3 in front there. So I can see that my nitrogens, my oxygens, as well as my hydrogens are balanced. So this is the one reaction that we have. The other one that you could have also given us would have been your nitrogen dioxide that reacts in the presence of oxygen with water. Okay, so there's oxygen involved over here. This is in a gas form, this is in the gas phase, this is in the liquid phase. So if I then go and I look at my reaction that takes place, all 3 of these reactants will produce one product and is going to give me my nitric acid over there. Now if I quickly go and I look at my balancing over here, there's 1 hydrogen, 2 hydrogens over here. So if I bring in the 2, I will see that my hydrogens are balanced. Now I see I've got 2 nitrogens. I only have 1 nitrogen over here. If I bring in the 2, I find that that is balanced. And I go and I see, okay, now I have 6 oxygens over here. 2 times 2 is 4, plus 2 is 6, plus another 1 is 7. So I need to go and relook my balancing. So I start over again. And this happens quite often in the exam. So just remember, as teachers, after the 3rd or 4th class, we remember what the balancing of the equation looks like, and we just go and write it down. So let's see if we increase the number of hydrogens over here, if it will help us to balance the equation. Now I see I've got 4 hydrogens. If I bring in the 4 on this side, I will have 4 hydrogens over here as well. 2 times 2 will give me 2 oxygens, plus 2 is 6 oxygens. 2 plus 2 is 4 oxygens, plus another 2 is 6. 4 times 3 is 12. So I need to double something over here. I need to increase a value. And if I bring in a 4 over here, it balances my nitrogens. And at the same time, I now have 8 oxygens, plus 2 is 10. Plus another 2 that I have over there is 12. And 4 times 3 is 12. So I can see that I've balanced my equation over there. So in this case, there were 2 possible balanced equations that you could have given us. Either one of them will be accepted in the exam. Just remember that for this specific type of question, it's worth 3 marks because you get a mark for your reactant, your mark for your product, and then for your balancing overall. So even if you struggle with the balancing, just giving us the reactants and the correct products over there is already scoring you 2 out of 3 marks. Now I'd rather have 2 out of 3 than 0 out of 3 because I leave out the question because I'm scared I'm not going to balance it. Remember, it's all about putting together little bits at a time. 1 mark here, 1 mark here, 1 mark here, and eventually
everything
going
counts,
to add it.
Yeah.
Absolutely.
Yeah.
Okay, question 8.3. Now they tell us that high levels of nitrogen dioxide in the atmosphere can result in damage to crops and eventually food shortages. Try and say that. All right, briefly state how high levels of nitrogen oxide can damage these crops. Now remember, right in the beginning we said if the nitrogen dioxide dissolves in the rainwater, it is going to form nitric acid. Now this nitric acid, even if it's diluted, can still damage the crops. If the acid rain comes down onto the crops on the plants, it affects the leaves, it burns the plants, so it's going to cause the decay in the plants. You're not going to have a proper crop harvest that comes through, and if you don't have that proper harvest, you have weak crops. You're going to have food shortages because no one's going to want to buy your produce. So over here, what you can say over here, that the nitrogen dioxide will form nitric acid in the rain, this acid rain that we have over there is then going to damage the crops. So acid rain damages the crops, or you could say that it burns the plants. All right, now you'll see that the question over here asks you just to state how the high levels will affect it. So you only have to tell us what's going to happen. You don't have to go into any lengthy explanations over there with this question. If we move on to question 8.4, let's just change our pen color. They tell us that the nitric acid can cause corrosion of copper cables, whilst hydrochloric acid does not harm the copper cables at all. Refer to the relative strengths of the oxidizing agents involved to explain this phenomenon. Now, if you go and you look at it, you have nitric acid, which is HNO3, and over here you've got your hydrochloric acid, which is HCl. Now, in this case, your active agents over here, your oxidizing agent, would be the nitrate, the NO3, or the Cl for the hydrochloric acid. And if you go and you look at that standard potential table that John used just previously, if you go and you look over there, and you will notice that NO3 has got a higher oxidizing ability than the chlorine, because we find it higher up on the standard potential chart. Sorry, I struggle with the English today.
No, it's okay.
All right, so the standard potential chart. So if you go and you look at it, it is. Let's try and say that after Sunday lunch.
Yeah.
So what we're looking at over here is that the NO3, for your answer over here, is going to have a higher oxidation ability. Whereas, and over here, the hydrogen will not have the same, or have such a high oxidizing ability. Okay. Let's move on to the next question. All right, so if we go and we look at question 8.5, now we get into the KC question, and this is exactly what you guys have all been asking for.
Is this the big important part?
This is the big important part.
Okay.
All right. I know John has been teaching you to use the table method, which is excellent, and he's been using the acronym RICE. So we're going to stick to that.
Somebody actually said to us on Twitter that they should use RICE, and I have retweeted it. So hopefully all of you that are following on Twitter, check out that comment, check out what RICE is, and I'm sure Zelda's about to probably explain.
Yeah.
Cool.
Okay, so the information that give us is we start off with 2 mole of NO2 and an unknown amount of N2O4 gas that are sealed in a container. Now the volume for my container is 2 cubic decimeters, and it is fitted with a plunger at a certain temperature. Now remember, plunger is like a syringe. When you press it, it's going to increase the pressure on the inside, and then the following reaction takes place. We see that the NO2 changes into N2O4. Let's just change our subscript over there. Okay. Now, they want us to know what is going to, or they tell us that the concentration at equilibrium is 0,4. And they want us to go and calculate what the equilibrium constant at this temperature is 2. Sorry, that's your equilibrium constant. So there's our concentration, there's our equilibrium constant. So now they ask us to go and find the initial amount of the N2O4. Now if you go and you look over here, you have 1 reactant and 1 product, which means that your table will have 2 columns, apart from your column with your headings. So on the one side, you're going to have your NO2, and here you will have your N2O4. Okay, so that's important that you start off over there. Now, the RICE, if I can quickly do this. The R stands for the ratio, okay? So let's do the R in a different color. The ratio that we have Now this ratio we're going to get from our balanced equation. And thank goodness they gave us an already balanced equation, so it's easy for us to see. Remember, if there's nothing written in front of the molecule, it's a mole of 1. And there's a 2 mole over there, so that is our ratio, is a 2-to-1 ratio that we're dealing with. And they tell us that initially we've got 2 mole of NO2 and an unknown amount of nitrogen, or N2O4. So your initial number of moles. Okay, now the initial number of moles over here for this one was 2. Sorry, I need to just get my information. And this one is unknown. Anything unknown, we make X. Okay? The next one we have over here is C. Now, I'm not sure what John uses the C for, but I teach my children that that's the stuff that is consumed, all right, or converted, or used during the reaction. So this is your converted moles. And for this, you're going to need the ratio. Okay, and then lastly, the E stands for your equilibrium. And over there at the equilibrium, that is going to be the number of moles. And also important over here is the concentration. So your concentration at equilibrium is important over here. And if ever you got easy marks, this is the easiest marks to remember, just to put this formula in here, because this formula automatically scores you 1 mark over there in your table. Okay, so now let's look at your information. We see that we've now got the 2 over here, the 1. The initial number of moles was 2, and they want to know from us what was used over here. Now, if we go and look, we had 2 moles initially, and they tell us that our N2O4 increases by 0.6. So at the end, at equilibrium, we know that for our products, we add them together. So products, we add, and for our reactants, we're going to subtract. Right, I'm just writing there on opposite ends of the screen. So over here, I'm going to subtract whatever amount I consumed. So if I have, for this side, my equilibrium is going to be the sum of those 2 columns. So it is going to be the X plus 0.6. Now, if I go and I look at this, just very quickly, they tell me that my concentration of the NO2 at equilibrium is 0.4. So my concentration over here is the 0.4 that I've got there. Now I need to use this concentration together with the volume to go and find the number of moles at equilibrium. Now I can do it in my table, I just don't have enough space. So I'm just going to do it at the bottom and fill it in over there. The concentration is the number of moles divided by the volume. They told us that the concentration is 0.4. The number of moles, the volume was given to you as 2 cubic decimeters. Okay, so if I multiply that across, my number of moles works out to be 0.8 moles at equilibrium. Okay, I'm going to substitute this back into my table. So all the way from there, I bring it in, and I've got my 0.8 over there. Now, if this is what I had and this is what I'm left with, I need to find out how much was used, and that is where I'm going to subtract them. So 2 minus the 0.8 is going to give me 1.2, and that is the amount that you used. And those values are in there, but what we are interested in over here is to work with the concentrations. So number of moles over here. Now, this number of moles was given to us. For this one, we need to go and work it out, and I'm just creating space over here. Remember that the number concentration is the number of moles over the volume. In this case, we don't know, but we've got an expression that we can add over here. And we're going to divide it by the volume of 2. So these 2 you will use in your Kc expression. Now, if I'm going to go to the Kc expression, I've got all the information from my table. I'm just making space on this side. Remember, your Kc expression is an expression of your product over your reactants. So your product in this case is the N2O4, square bracket. So that's the concentration of your product. And over here you have the concentration of your reactant. Now that 2 that you had in front over here, if you go back to your formula, the 2 that you had in front over here is now going to become your exponential value. So you're going to put that 2 at the top over there. Then substitute in your concentrations. For the top one, it is going to be your X plus 0,6 divided by 2, divided by, in this case, your concentration for the NO2 is going to be 0,4 squared. And if you put all of that into your calculator, you should get the following value over here, which is 0,04 mole. Now with nowadays, you've got, guys all have the scientific calculators, so you can actually, as the fraction is written over there, type it in on your calculator to see the value as it appears over there. We just haven't brought out our calculator, so it's difficult for me to just go back into the files and pull it out for you. But that's the answer that you're going to get there. So if you go and type it in, remember, your X is going to be your unknown, so you're going to have, you know, put all of this into your calculator as a fraction. Just what I forgot to mention over here, they tell us, I see now my calculation is incomplete, that the equilibrium constant is 2. So I should have brought in the 2 over here. Okay, so if I bring in the 2 over here and I work it to an X, then I should find that my X over there is 0,4. So therefore, the number of moles of my N2O4 in the beginning, or that is used, is going to be 0,04 mole. All right, okay.
Okay, guys, I'm so sorry, but we've run out of time.
Yeah.
I've been going, Zelda, we have to go.
We have to go, sorry.
Guys, I know that you all have a lot of questions on KC. Keep them coming on Facebook, and we'll see what we can try and do. We'll see if John or Zelda can help. Maybe we can just post a little thing that'll, you know, help the confusion. But we have to go, and good luck for your test tomorrow. We are behind you, class of 2011. You guys are going to rock.
Yeah, you guys are going to do great. And
Yeah,
you're going
you
to do
guys-
well. I'm sure you're well prepared, and you're going to
You know
ace
your
this.
work. You know your work.
Stay
Okay?
calm, stay focused, and just go and do it.
Okay. Until then, good luck, and we'll see you next time. Bye.
Bye.